So what we have done till now, that we try to understand what is the pack capacity, what is the pack heat load, various modes of thermal management system. Then we have solved few examples where we have found out heat loads. Then in using passive thermal management system, what could be the PCM. We have also understood what are the sensors being used, why the temperature is important. Now we will do some case studies based upon that what we have worked out in our lab, and using the simulation model, and that is what I am going to show you for next couple of minutes. A cell does not have uniform thermal conductivity in all directions. In X, Y and Z direction it could be same or it could be different, and that can be either tested into the lab or we can get it from the manufacturers. If there is a single cell, that may not be that much of important, but in a battery pack you have a stack of cells. So you need to identify the locations where you have a more heat generation and to transfer the heat from that place, and that's only possible when you know what is the thermal conductivity in each and every direction. Then only you would be able to identify the hot spots. If it is same in all directions, then it is easy. If you have directional thermal conductivity, then what happens? That is what we are going to see now. What we have done, anisotropic thermal conductivity due to stacked layer of good and poor thermal conductivity layers in the calendar. Free convection in 6 cells, 1, 2, 3, 4, 5, 6 cells with the following configuration: steady state simulation. The density is 1600 kg per meter cube, ambient temperature 35 degree, ambient heat transfer coefficient 10 watt per meter square K, because we are considering mostly it is a natural convection. 0.5 mm thick insulation pad between every 2 cells, because what you see, we were making 2 P16S packs. So after every 2 cells we have to electrically insulate. So 0.5 mm thick insulation pad is inserted, like here and here and also here and also at the last. 1C discharge rate, impedance of the cell is 4 milliohm for this particular simulation. So 14 ampere into 14 ampere square into R, and per cell heat generation is 0.784 watt. Now two conditions. In first condition, the thermal conductivity of 100 watt per meter K in all the directions, and in second case is a 30, 30 and 0.9. The specific heat is same. When we have isotropic thermal conductivity, what we see at the center, we have the highest temperature. When we have anisotropic in all 3 directions, we still have the highest temperature at the center, but temperature uniformity in the case of isotropic thermal conductivity is much better than anisotropic. So now I have a hot spot here. However, this hot spot is spreaded over several layers. So if we are not able to identify this type of situation, I may not be able to design my battery pack sufficiently for the internal temperature gradients. When I say internal temperature gradient, what you see in the case 1, the temperature gradient is 0.5. That means whole 6 cells is almost at the similar temperature. That means whatever degradation is happening in one cell because of the temperature, it is same in all the cells, almost same. But if you see the second case where we have anisotropic thermal conductivity, in that case my temperature gradient is as high as 3 degree. It is still within the limit, but this cell will degrade faster than this cell, because this cell is 3 degree higher temperature than this cell. And in a battery pack, the weakest cell is what makes the whole battery pack at the same level. That means every whole battery pack would be at the weakest cell level. If this cell is degraded faster than any other cell, that means the whole pack has a capacity, current, voltage, all the limitation by this cell, posed by this cell. Even though this cell is good, but the whole pack capacity would be calculated based upon this cell. So we do not want this temperature differential to happen, so that I will design this pack in such a way that my temperature distribution or temperature gradient within the cells is minimum, like what is the case of isotropic thermal conductivity. I will try to maintain with 0.5, but then I have to redesign. The same design does not work here. I have to redesign in such a way that even this 3 degree can go down to 0.5, because now we know that this is the ideal condition, this is the actual condition, and that happened only because of anisotropic thermal conductivity. The another case study, bus bar ohmic heating simulation, which we have a part of that we have discussed in the electrical design, and then we will discuss it here. Now what we have done is we use a 4P bus bar, that means 4 parallels, 1, 2, 3, 4, and the net current is 56 ampere. Material copper, 0.2 mm thick, electrical conductivity dependent, temperature dependent, ambient temperature 25 degree centigrade, convective heat transfer coefficient because of natural convection 10 watt per meter square per Kelvin. The initial temperature was 25 degree centigrade. Steady state simulation. But if you see here, now it has reached to 45 degree. In fact, whole the bus bar is between 42 to 45 degree, but at the central region has reached to the 45 degree centigrade. And this area, why it has reached, the two regions. One is high electric current density here, and also less convective path here. So let us observe, this is a current flow across the holes, like these holes what we are showing. Yeah. Now electrical current density is almost, except few places we see it is quite uniform. So what simulation shows, average current density is 7.041 ampere per mm square. Corner of the center tab shows higher current density. The thickness of bus bar should be increased to 0.5 mm to reduce the current density below 5 ampere per mm square. Now another important thing is electronics. We were talking about current parallelization. So now I have 30 ampere current to be passing on in the solid state switches, flow in, flow out. Now these switches like MOSFET poses resistance to the current flow and generate waste heat. To expect no failure or higher lifetime, this component must work within limited temperature window. If your temperature is exceeding first of all your lifetimes comes down. The second, it may fail after some particular temperature. What we have done some steady state simulation on MOSFET with a resistance of, obviously it is not a steady state, it has to be transient by nature of the battery pack, but to understand it quickly, MOSFET resistance is 2.3 milliohm, current 7.5 ampere, and what we want, the MOSFET temperature should not exceed 70 degrees centigrade. So total 8x MOSFET with and without heat sink. So this is without heat sink and this is with heat sink. In the case 1, where we do not have heat sink, the temperature has gone to 68.3 degrees centigrade. Where we have heat sink, the temperature is 58.3, exactly 10 degree temperature difference. So after including the heat sink, what happens? The temperature difference has come down to, or the peak temperature has come down by 10 degrees centigrade. Now, for every 10 degrees centigrade increase in the temperature of electronics, generally life of the electronics become half. What it means? If my electronics, let us suppose the resistors work 1000 hours at 45 degree ambient or 45 degree temperature, not ambient, temperature of the resistor. If the resistor temperature is maintained at 55 degree, it will give you only 500 hours life. So every 10 degree decrease in the temperature of electronics would give you twice the life. Now, by using just simple, even though failure temperature is 70 degrees centigrade, it would not have failed, but by providing a simple heat sink, the temperature has come down to 58.3 and my life of MOSFET has become twice now. So hence the additional heat sink would allow the MOSFET to have twice the life comparing to without heat sink MOSFET, and that helps in improve the reliability of BMS. Now another question comes here. We were also talking about the current parallelization path. What will happen if these two MOSFETs get 6 ampere each and these two MOSFETs gets 9 ampere each? So if my current is not parallel in each of the MOSFET, think it is a homework. The next is module thermal management. The battery pack is discharged at 1C rate, the same 2P16S battery pack. For different thermal management system, what we have tried here, we compared all the 3 different thermal management system: natural convection, forced air cooling and cold plate, or what you say, hybrid cooling system or direct expansion type of cooling system. And all these 3 cases has been compared for the maximum cell temperature. The boundary conditions, again we have done a steady state because it is quite quick, it is much faster than the transient simulation. Ambient 35 degree centigrade. For convective heat transfer, 2 watt per meter square per Kelvin for natural convection, 30 watt per meter square per Kelvin for forced convection. Cold plate is at 17 degree centigrade in the case of third thing, cold plate cooling. Heat generation in each cell is 0.9 watt. In natural convection, the maximum temperature has reached to 52 degree centigrade. In case of forced convection, the maximum temperature is 40 degree centigrade. My ambient condition is 35 degree. 12-degree temperature difference by just blowing the air properly at 35 degree. In cold plate cooling, my maximum temperature is 24 degrees centigrade. So, if it is a very big battery pack, let us assume, what mode would have been best for us? Obviously, active cooling system, because it is maintaining the temperature what I wish. If that is not possible, let us suppose for a smaller battery pack, what would I prefer? If ingress protection is not mandatory, what I would have preferred? I would have gone for the forced convection. Because it is still able to maintain the temperature much below than the natural convection. But if all the requirements of ingress protection and all the things come, then I do not have any other option to have a proper natural convection. In that case, my temperature can go up to 52 degrees centigrade. I will get less life, but I do not have much other options available. So, let us summarize the thermal design of a battery pack. A good thermal design increases the pack efficiency by maintaining the temperature at optimal band of 15 to 35 degrees centigrade. It improves the life of the battery pack drastically. Something between, you would have seen 300 to 2300 cycles. That much impact comes if we do not maintain the thermal management system properly. It helps in accident prevention, mitigates any such situations come. To cell, by maintaining the temperature, it does not allow the cell to go any thermal accident like thermal runaway. Even if that happens, it try to isolate. If a proper thermal management system is there or proper thermal design is there, it try to mitigate, not to spread further. Bus bar, by maintaining a proper thermal management or proper thermal design, does not allow it to go any further a temperature which is not safe. Electronics, it helps in making it more reliable and more fail safe. It should be kept, a thermal design or thermal management system should be kept as simple as possible. You unnecessarily complicate, that would come back as a cost to you in service, as a failure, more failure. So, it should be as simple as possible. Wherever possible, utilize a passive thermal management system because it does not take any energy from the pack. If not possible or does not help in saving the cost because of the battery degradation, active thermal management system, but then again should be simple. Is it possible to have only forced air cooling system? Yes, if that helps. Liquid cooling system? Yes. I am talking about increasing the complexity, direct expansion or hybrid type. This all depends upon what is the pack life we wanted and what is the cost of running this thermal management system. Should have low parasitic power consumption because it takes energy from the pack. So, its impacts on your range. Easily serviceable, that further reduces the cost of operation. We select the various material of thermal management system based upon its thermal properties, mechanical stability and the cost. So, with that we finish our thermal design of the battery pack. Any question? Next class we will do battery management system and embedded system.